IP multicast is a method of sending Internet Protocol datagrams to a group of interested receivers in a single transmission. It is often employed for streaming media applications on the Internet and private networks. The method is the IP-specific version of the general concept of multicast networking. It uses specially reserved multicast address blocks in IPv4 and IPv6. In IPv6, IP multicast addressing replaces broadcast addressing as implemented in IPv4. IP multicast is described in RFC 1112. IP multicast was first standardized in 1986. Its specifications have been augmented in RFC 4604 to include group management and in RFC 5771 to include administratively scoped addresses. Technical description, overview. IP multicast is a technique for one-to-many and many-to-many real-time communication over an IP infrastructure in a network. It scales to a larger receiver population by requiring neither prior knowledge of a receiver's identity nor prior knowledge of the number of receivers. Multicast uses network infrastructure efficiently by requiring the source to send a packet only once, even if it needs to be delivered to a large number of receivers. The nodes in the network take care of replicating the packet to reach multiple receivers such that messages are sent over each link of the network only once. The most common low-level protocol to use multicast addressing is User Datagram Protocol. By its nature, UDP is not reliable. Messages may be lost or delivered out of order. Reliable multicast protocols such as Pragmatic General Multicast have been developed to add loss detection and retransmission on top of IP multicast. Key concepts in IP multicast include an IP multicast group address, a multicast distribution tree and receiver-driven tree creation. An IP multicast group address is used by sources and the receivers to send and receive multicast messages. Sources use the group address as the IP destination address in their data packets. Receivers use this group address to inform the network that they are interested in receiving packets sent to that group. For example, if some content is associated with group 239.1.1.1, the source will send data packets destined to 239.1.1.1. Receivers for that content will inform the network that they are interested in receiving data packets sent to the group 239.1.1.1. The receiver joins 239.1.1.1. The protocol typically used by receivers to join a group is called the Internet Group Management Protocol. With routing protocols based on shared trees, once the receivers join a particular IP multicast group, a multicast distribution tree is constructed for that group. The protocol most widely used for this is protocol-independent multicast. It sets up multicast distribution trees such that data packets from senders to a multicast group reach all receivers which have joined the group. For example, all data packets sent to the group 239.1.1.1 are received by receivers who join 239.1.1.1. There are variations of PIM implementations: sparse mode, dense mode, source-specific mode and bidirectional mode. Of these, PIM-SM is the most widely deployed as of 2006. SSM and BIDER are simpler and scalable variations developed more recently and are gaining in popularity. IP multicast operation does not require an active source to know about the receivers of the group. The multicast tree construction is receiver-driven and is initiated by network nodes which are close to the receivers. IP multicast scales to a large receiver population. The IP multicast model has been described by Internet architect Dave Clark as, you put packets in at one end, and the network conspires to deliver them to anyone who asks. IP multicast creates state information per multicast distribution tree in the network. If a router is part of 1,000 multicast trees, it has 1,000 multicast routing and forwarding entries. On the other hand, a multicast router does not need to know how to reach all other multicast trees in the Internet. It only needs to know about multicast trees for which it has downstream receivers. This is key to scaling multicast addressed services. It is very unlikely that core Internet routers would need to keep state for all multicast distribution trees, they only need to keep state for trees with downstream membership. In contrast, A unicast router needs to know how to reach all other unicast addresses in the Internet, even if it does this using just a default route. For this reason, aggregation is key to scaling unicast routing. Also, there are core routers that carry routes in the hundreds of thousands because they contain the Internet routing table. Routing: each host that wants to be a receiving member of a multicast group must use the Internet Group Management Protocol to join. Adjacent routers also use this protocol to communicate. In unicast routing, each router examines the destination address of an incoming packet and looks up the destination in a table to determine which interface to use in order for that packet to get closer to its destination. The source address is irrelevant to the router. However, in multicast routing, the source address is used to determine data stream direction. The source of the multicast traffic is considered upstream. The router determines which downstream interfaces are destinations for this multicast group, and sends the packet out through the appropriate interfaces. The term reverse path forwarding is used to describe this concept of routing packets away from the source, rather than towards the destination. A number of errors can happen if packets intended for unicast are accidentally sent to a multicast address. In particular, sending ICMP packets to a multicast address has been used in the context of DOS attacks as a way of achieving packet amplification. On the local network, multicast delivery is controlled by IGMP and MLD. Inside a routing domain, PIM or MOSPF are used. Between routing domains, one uses inter-domain multicast routing protocols, such as MBGP. The following are some common delivery and routing protocols used for multicast distribution: Internet Group Management Protocol, Protocol-Independent Multicast, Distance Vector Multicast Routing Protocol, Multicast Open Shortest Path First, Multicast BGP, Multicast Source Discovery Protocol, Multicast Listener Discovery, GARP Multicast Registration Protocol, Shortest Path Bridging, Layer 2 Delivery. Unicast packets are delivered to a specific recipient on an Ethernet or IEEE 802.3 subnet by setting a specific Layer 2 MAC address on the Ethernet packet address. Broadcast packets make use of a broadcast MAC address, which includes setting the broadcast multicast bit in the address. IPv4 multicast packets are delivered using the Ethernet MAC address range 01005E, 000001005E, 7F, FFFF. This range has 23 bits of available address space. The first octet includes the broadcast multicast bit. The lower 23 bits of the 28-bit multicast IP address are mapped into the 23 bits of available Ethernet address space. This means that there is ambiguity in delivering packets. If two hosts on the same subnet each subscribe to a different multicast group whose address differs only in the first 5 bits, Ethernet packets for both multicast groups will be delivered to both hosts, requiring the network software in the hosts to discard the unrequired packets. For IPv6 multicast addresses, the Ethernet MAC is derived by the 4 low-order octets AUT with a MAC 3333000000. So for example the IPv6 address FF02, deadbeef 13 would map to the Ethernet MAC address 333300000103. If a switch does not understand multicast addresses, then it will broadcast traffic sent to a multicast group to all the members of a LAN. In this case the system's network card has to filter the packets sent to multicast groups they are not subscribed to. There are switches that listen to IGMP traffic and maintain a state table of which network systems are subscribed to a given multicast group. This table is then used to forward traffic destined to a given group only to a limited set of hosts. This is done through the use of IGMP snooping. Additionally, some switches with Layer 3 capabilities can act as an IGMP querier. In networks where there is no router present to act as a multicast router, a switch with IGMP snooping enabled can be used to generate the needed IGMP messages to get users to subscribe to multicast traffic. Wireless considerations, like Ethernet, 802.11 uses the same range of MAC addresses to map IP multicast addresses. However, an 802.11 wireless network will handle multicast traffic differently, depending on the configuration of delivery traffic indication message, and beacon interval settings. If no stations within the basic service set are in power save mode, multicast packets are sent immediately when they arrive. If there are one or more stations in power save mode, access points then only deliver multicast traffic after each DTIM interval, and transmit at one of the supported rates in the basic rate set. In most retail wireless access points routers, this interval is either 102.4 ms or 204.8 ms, and the transmit rate is either 1 Mbps or 6 Mbps, depending on the operating band and protection mode. As a result, the DTIM and beacon interval settings should be adjusted for optimum performance when implementing multicast in wireless networks. Unlike Ethernet, most traffic in 802.11 is sent reliably using ACKs and NACKs so that radio interference doesn't cause unbearably high packet loss. However, multicast packets are sent once and are not acknowledged, so they are subject to much higher loss rates. There are various methods for coping with this, such as choosing to unicast multicast data repeatedly to each client, or requesting ACKs from each client. Some methods require only modification on the access point, and are supported in some enterprise-class devices, while other improvements would require modifications to clients, and therefore have not seen widespread adoption. Reliable multicast, by its very nature, is not a connection-oriented mechanism, so protocols such as TCP, which allows for retransmission of missing packets, are not appropriate. For applications such as streaming audio and video, the occasional dropped packet is not a problem. But for distribution of critical data, a mechanism is required for requesting retransmission. One such scheme, proposed by Cisco, is PGM, documented in RFC 3208. In this scheme, multicast packets have sequence numbers, and when a packet is missed, the recipient can request that the packet be re-multicast with other members of the multicast group, ignoring the replacement data if not needed. An expanded version, PGMCC, has attempted to make IP multicasting more TCP-friendly by stepping the entire group down to the bandwidth available by the worst receiver. Two other schemes documented by the Internet Engineering Task Force are the Standards Track Protocol and ACK-oriented reliable multicast, documented in RFC 5740 and RFC 5401, and the Experimental Protocol File Delivery over Unidirectional Transport, documented in RFC 6726. Open source, in addition to proprietary, implementations exist for these. Other such protocols exist, such as Scalable Reliable Multicast, and are defined by a variety of sources. Such protocols vary in the means of error detection, the mechanisms used in error recovery, the scalability of such recovery, and the underlying ideas involved in what it means to be reliable. A list of reliable multicast protocols from the ACM's SICA Multicast Workshop, August 27, 1996, documents a number of approaches to the problem. Independent groups like the Internet Protocol Multicast Standards Initiative have claimed that the lack of a truly scalable, secure, reliable IP multicast protocol like the proposed Secure Multicast for advanced repeating of television have hampered the adoption of IP multicast in inter-domain routing. The lack of a widely adopted system that has AES-level security and scalable reliability have kept mass media transmissions of sporting events and/or breaking news events from being transmitted on the public Internet. Reliable IP multicasting protocols, such as PGM and SMART, are experimental. The only standards track protocol is norm. Multicast-based protocols, since multicast is a different transmission mode from unicast, only protocols designed for multicast can be sensibly used with multicast. Most of the existing application protocols that use multicast run on top of the user datagram protocol. In many applications, the real-time transport protocol is used for framing of multimedia content over multicast. The resource reservation protocol may be used for bandwidth reservation in a network supporting multicast distribution. Multicast DNS can be used to resolve domain or host names without a dedicated DNS server by using multicast. Deployment: IP multicast is widely deployed in enterprises, commercial stock exchanges, and multimedia content delivery networks. A common enterprise use of IP multicast is for IPTV applications such as live television distribution and televised company meetings. In the hospitality industry, IP multicast has become common for IPTV television distribution in hotels, and in the retail sector IP multicast is now widely used for TV distribution and video advertising applications. Pay TV operators and some educational institutions with significant on-campus student housing have deployed IP multicast to deliver one-way streaming media such as high-speed video to large groups of receivers. Additionally, there have been some uses of audio and video conferencing using multicast technologies. These are far less prevalent and are most often relegated to research and education institutions, which often have a greater degree of network capacity to handle the demands. Some technical conferences and meetings are transmitted using IP multicast. Until recently, many of the sessions at the IETF meetings were delivered using multicast. Another use of multicast within campus and commercial networks is for file distribution, particularly to deliver operating system images and updates to remote hosts. The key advantage of multicast boot images over unicasting boot images is significantly lower network bandwidth usage. IP multicast has also seen deployment within the financial sector for applications such as stock tickers and Hoot-and-Holler systems. While IP multicast has seen some success in each of these areas, multicast services are generally not available to the average end user. There are two major, related, factors for this lack of widespread deployment. First, forwarding multicast traffic imposes a great deal of protocol complexity on network service providers. Second, core network infrastructure exposes a far greater attack surface, with particular vulnerability to denial of service attacks. RFC 3170 provides an overview of deployment issues. History, development. IP multicasting was first developed by Steve Deering while at Stanford University, for which he received the IEEE Internet Award. The MBONE was a long-running experimental approach to enabling multicast between sites through the use of tunnels. While the MBONE is no longer operational, there is renewed interest in tunneling multicast traffic once again in order to make the service available to a wide array of end users. Commercial deployment. Starting in 2005, the BBC has begun encouraging UK-based Internet service providers to adopt multicast addressable services in their networks by providing BBC radio at higher quality than is available via their unicast-addressed services. This has also been supported by a variety of commercial radio networks, including BBC, GCAP Media, EMAP and Virgin Radio. The German public service broadcasters ARD and ZDF and the Franco-German network ART offer their TV program multicasted on several networks. Austrian internet service provider Telekom Austria offers its digital subscriber line customers a TV set-top box that uses multicast addressing and receiving TV and radio broadcasts. In Germany, T-Home, a brand of Deutsche Telekom, offers a similar service. IP multicast software. Media Tools Repository, UK, UCLA a collection of tools for Thembone. Videolan a free software multicasted video streaming application. Xorpa a free software router with multicast support. Smcroot, Debian a simple tool to manipulate multicast routes on the Linux kernel. SSMping, NO, Vina a tool to test multicast connectivity. Wilbert, IGMPv3, Klosterhofer a host implementation of IGMPv3 on FreeBSD. IP Multi, Palo Alto, Xeroxa, Java Reliable Multicast Service libraries and services for building multicast-aware applications, PIM implementation, USCO an implementation of the PIM protocol, now obsolete, QPIMD a PIM daemon for Quagga, a PIM module for the Quagga routing suite. Gated, Next Hope a Unix implementation of routing protocols, including multicast. PIMDM code for Gated, University of Oregon. Norm, NRLA a NAC-oriented reliable multicast from the U.S. Naval Research Laboratory, with an open-source C++ implementation, ECMH, Unfix a IPv6 multicast daemon, allows IPv6 multicast to be used without the need for PIM. MRD6 a Euro IPv6 multicast routing daemon, UFTP a Euro encrypted UDP-based FTP with multicast, Xstreamer a Euro a free software multimedia framework that supports multicast video streaming, Mac proxy, INET Research Group a Euro an IGMP MLD proxy that supports PM IPv6 multicast extensions, see also, shortest path bridging, dense multicast, sparse multicast, source-specific multicast, core-based trees, IGMP snooping, multicast address, multicast, notes. References. External links, Multicast over TCP/IP, the GNU Linux Documentation Project, March 1998a. Describes multicast in the Linux kernel, although some sections is outdated and does not cover recent software. Reliable multicast transport, IPv4. Multicast and unicast group membership, IPv4. Protocol independent multicast, IPv4. Source-specific multicast, IPv4. Multicast security, IPv4. Multicast, SOCTA. IP details. IP Ethernet multicast, CX, Firewaller. IP multicast, Cisco. Overview of reliable multicast methods, ACM SICA Multicast Workshop, University of Massachusetts, August 27, 1996a. Floyd, a reliable multicast framework for lightweight sessions and application-level framing, ISARA. The paper defining scalable reliable multicast. Multicasting, Multicast Tech, retrieved 2010-11-18a. An analysis of multicast methods, Tech Talk, Wikidata.